All right. Uh, Welcome everyone. Lecture 3, area theory class, fifth class. We're going to talk about first the material, which was value and policy iteration that you were supposed to read about. So we start with a short summary of um, of the material that you were supposed to read about. And it's going to be in a slightly different order than in the lecture notes or than it was in the previous year's lecture. So I start with this result that so hidden in this result is that we have this finite state action MDP discounted, uh, and there's no other condition. And we take any function v which maps states to reals, and we take a greedy policy with respect to it. So greedy just means that if you do one step bam on look ahead, um, performing that, you're choosing the action that maximizes these look ahead, one step look ahead values. And then you can show with a little calculation using just contraction properties of the operators involved that the value function of the policy that we get this way is going to be almost optimal to the degree that the function that you picked differs from the optimal value function. So here V star is the optimal value function. V is this function that you got. And this is sort of a continuity result, the way I like to look at it, or it's just one-sided, but it's sort of like the or sensitivity result, if you wish. So there is the space of value functions, um, and that's RS. So here is the first state, state one. Here's the S state, and this is my representation for the high dimensional value function space. And let's say the rewards are non-negative, then all the value functions would be just like points in this space. So this is R to the power of S. They're all points in this space. And as it happens, the space of value functions has a funny structure. If you, oh, okay. Ooh, let's figure this out. How do I use this? I want to erase. They keep changing the software. Okay, there you go. Okay. Okay. Uh-huh. Yep. Okay. That was not the best choice, but it does work. So there are all these value functions for all the policies, and they happen to have a funny structure. So first of all, it happens to be true. It was not part of the lectures. That this set is convex. It's beautiful. And the second is that it's not a convex set that would look like this. It's a convex set, and that's part of the lecture, if you think about it, such that if you would calculate like the corners of the minimum enclosing rectangle of this, then there is the upper right corner and the lower left corner of this rectangle. In high dimension, a rectangle it has, like many dimensions, but it's still a rectangle. Then these points belong to the set. So these are all have to be all valid value functions. So the value function space kind of looks like this. So if there was some value function there, this has to be all in, this has to be all in, this is all in. It's kind of funny. This is V star here. So that's the value that you would get if you maximize for each state independently of each other, right? So the minimum enclosing rectangle's up right corner has this property. And this is the value that you would get if you minimize. Well, we never think about minimizing because we're talking about rewards, but if you just think about, oh, these were costs, you could change the theorem and it would just, like, we had this theorem that said that there exists a policy that whose value function is equal to this V star. So this point has to be in the space of value functions. This point also has to be in the space of value functions. We never proved that this set is convex, but it happens to be convex, and there was a nice paper just last year or 2 years ago, maybe. Uh, First author is Dabashi, and um, Dale was involved, and some other folks were involved. They proved that this space is convex. It's kind of a neat result. It's good to remember this picture. Anyways, so what's the relationship to this result that we're talking about here? Let me choose some other color. So this result says that if we choose some other value function v, well, we may be choosing, I don't know, this one here. It may not be, it's just a function, it's just a point in the space. It may not be within this value function polytope. Then after that, we choose, so this is just v. After that, we're going to choose a greedy policy. So the policy is somewhere else. And we get a value function for that. So this value function, so that's going to be, I don't know, blue. And this v was the green guy. So this value function cannot be too far. So in particular, if you start to grow a box of equal sizes, it's a square from V towards V star. So whenever you get to touch one of the coordinates of V star, you stop. So that's like the size of the length of one side of the square is equal to this maximum distance between V and V star. So you get this maximum distance and you multiply it with 2 gamma times 1 minus gamma. So you inflate this maximum distance. This, let's say this distance was, wait, so you have to match all of them, right? So it's actually this. This is the maximum distance. This is smaller. Okay, so you have to inflate it by this factor, 2 gamma 1 minus gamma. So let's mimic that this is just, I don't know, 3. So then copy it 3 times, this length. And then you get this set, which is the set of all points in this RS space, which satisfy that, well, these points, I don't know, x, they are bigger than V star minus this 2 gamma 1 minus gamma times v minus v star. Infinity norm times 1. So this is this set. These points are here. And we can conclude that for the policy, which is greedy with respect to this value function, the value function of it lives in this space. Since it also lives in the polytope, it has to be part of this set. So it has to be here. So this is what geometrically this theorem is saying. And it's somehow, it's a continuity result, because if this goes to 0, if this distance goes to 0, then v pi is converging to v star, right? Because, well, this is going to get closer and closer and closer until it closes on v star. Okay? Exxon, you have a question?
Yes, I just wanted to ask for that convexity thing. Do we like do the states have to be connected to each other, or if like do we have this kind of assumption?
But there's no, it's a finite MDP, there's nothing.
Sorry.
No assumptions are needed, and the wave function space will be convex. It's quite intriguing.
So like with trap states, this also holds.
For what states?
With some trap states that don't affect, or like if like
Yeah,
in
like,
isolated
I mean,
states
like,
don't affect.
yeah, like if some states are completely disconnected from other states, then that's like a separate MDP. Then this set will have a product structure, right? Because you can independently change the values in one part of the state space and the other part of the state space. Then you have further structure, but if both of those sets are convex, the product of convex sets is going to be convex, so that cannot possibly cause any problem.
Okay, yeah, thanks.
It could just like add, but there is absolutely no condition on the MVP, so it's a very nice and good to remember is that it's not that often that it's useful, but sometimes it can be useful. This result, but it's good to keep in mind if you want to draw a picture in your head or like on paper about what is going on when we are trying to optimize, when we try to find a policy that's optimal. And it just means that like we are wandering within this red set, we are trying to get close to the upper right corner. And that upper right corner actually belongs to the set. So that theorem was the fundamental theorem, already guarantees that, right? So that was part of the previous lecture that said that V star is a fixed point, and if you take any policy that's greedy with respect to V star, that policy is optimal. So V star definitely belongs to this set. The definition of V star is that this is just like this upper right corner of this minimum enclosing rectangle. All right,
Yes.
Kushagra. Yeah. Oh, can I hear you? Wait,
Sorry,
I
am
think,
I audible now?
yeah,
Yeah.
you are. Yeah.
So I wanted to ask, in the lecture notes, the factor of two was not there. It was just gamma epsilon pi one
I
minus
copied this
gamma.
from the lecture notes.
Sorry.
I copied this
Oh no,
result.
not from the. I meant from the in the video in the recorded video.
Okay, in the video, maybe I made a mistake. The two is
Yeah,
the
we lost the 2 in the video. I think Chava mentioned he's like the result should have a 2, but then he didn't want to go back and find where the mistake was. But yeah, if you look at the lecture notes, it has the 2, like
Okay,
Chava
okay,
said.
yeah.
perfect. Thank you.
Sorry about this. Random people are calling me. I have no idea about who that was. All right, we are on no disturb mode now. Focus mode. Should have done that. All right. Um. All right. Let's move on. So this was the first result, and we're gonna rely on this result and versions of this result a lot. It comes up all the time. because you calculate, like the calculations are gonna go by calculating some value function. Maybe it's an action value function, maybe it's a value function. And then maybe greedifying, and then, okay, you wanna know, like, if you did a good job at approximating the optimal value function, is this going to be sufficient? And it turns out to be yes, up to this blow-up factor. And this blow-up factor is real, so you can come up with some examples where you see that it has to be real. It's like 2 states, whatnot. Not too hard to prove these things. Okay, so the next result is about value iteration, and so value iteration is this super simple way of calculating a sequence of these functions vk. You start, let's say, by 0, but you could start with any other point, and then you iteratively applying this operator t. So I wanted to draw a picture. Okay, because we love these pictures. So here's the first state. It is the S state. Here is your space of value functions, and we know that in order to draw this, well, it has to be convex, and like it can only have this like elaborate shape. Oh, the other thing I didn't mention about this is that all the corners, all these extreme points are at deterministic memoryless policies. No, I'm not going to the next line. All right, so this is the value. Okay. I guess don't draw on that side, because then PowerPoint wants to think that I'm trying to go to the next page. All right. So there are these extreme points. There cannot be more than how many deterministic memoryless policies we have. And then we start with a point. And let's say you start with the 0 point. Ooh, okay. Not that one. You start here. Start here. And you start to apply this operator t to this function. And it moves around, moves. And it's going to have some nice property. And the nice property it has is that if you calculate like how far it is in L infinity distance from this point V star, this distance for consecutive iterations is going to decrease by a factor of gamma. So that follows from the contraction properties of T, and because V star itself is a fixed point of this Bellman operator T. And so you do this, and then you can calculate quite easily for how long does it take to arrive at some function v of k such that it's at most within an epsilon distance to v star in the maximum norm. And the answer is going to be something like this. It's like the log 1 over epsilon 1 minus gamma divided by log 1 over gamma. And so that's kind of the iteration complexity of value iteration if you want to calculate an epsilon optimal approximation to the optimal value function. And calculating an epsilon optimal approximation to the optimal value function is a reasonable goal because of the previous result, because if we make the epsilon small enough, then the loss due to not knowing the optimal policy is going to be limited by this policy error bound. So you can just put together these two results and get a result on the complexity of calculations that you have to do with value iteration to get, let's say, an epsilon optimal policy, that optimal policy. So there is this factor here, this h comma epsilon factor, and you can show that there is the more precise factor that comes out of this calculation, this h star gamma epsilon, that is h gamma epsilon, which basically the same as the other one, except that log 1 over gamma is replaced by 1 over by 1 minus gamma in the denominator. That this is an upper bound on the other one, but the difference between the two is really small as compared to 1 over 1 minus gamma. So as gamma goes to 1, the difference becomes negligible compared to 1 over 1 minus gamma. And because of that, we often just like replace this log 1 over gamma factor in the denominator with this 1 minus gamma factor. And also, since this h gamma epsilon is an upper bound, and so if we require that the number of iterations is bigger than this guy, k is bigger than this guy, well, it has to be bigger than this guy too, then it follows that this number of iterations will definitely be sufficient to guarantee that the function that you read out is at most epsilon away from v star. So by the way, what would happen if you didn't start with 0? You would still have convergence towards v star. So all these, like you could draw these lines from every direction, just goes to v star. V star is the fixed point. You could draw this kind of vector field kind of representation. So you imagine that if you're following that field, then you very nicely just like bump into v star and you stay in place. And this is I don't know, like it happens pretty fast. It's like it happens geometrically fast. It's a nice picture too. All right, so
no, we tried that. So for the representation of the vector field, you can think of it as like a cone with like exponentially steep curves.
where is the cone?
Sorry, like so you have this like vector field, and no matter where you start in the space, you end up converging geometrically fast to this v star.
Sure.
And so maybe not a cone, but like a parabolic structure. I'm like yeah, sorry.
It can also be nonlinear, and it can be swirling, and like it's not necessarily that simple. It's like the one that I drew is probably misleading. So for example, even if you just have some fixed point calculation like this, but with linear stuff, like t would be just like a linear operator, okay? And it's a contraction, then very often it happens that the vector field is converging, but they are, like this orbits that are going around and around, and then like eventually they reach. So I don't know what you wanted to say, but maybe it's important to point out that the vector field itself can look in many different ways, but the point is that if you follow it, no matter where you start, you are geometrically fastly approaching V star, and V star is the only attractive point of this field.
I guess I was just trying to see, like, is this landscape convex? And what?
I don't know what you mean by the landscape being convex.
Like this vector field, like, because you say you can like swirl around, so you can imagine like you're approaching the star, but maybe you get stuck in what would be interpreted as like a flat area where the vector field is not that strong.
I mean, you are making progress, so there is this guarantee of making progress towards V star. So you will not slow down ever. There is no flatness, sort of. And you can also ask whether this is the gradient field of anything, and probably the answer is no, but I don't know the answer to that. If it was, if t was linear, then it would be the gradient field of the corresponding, I don't know, quadratic something energy surface, but and then it would be convex if this very nice convergence happens. So maybe that's what you're alluding to, but
Yeah.
this is non-linear, so I don't know.
Okay, mate. You said geometric convergence, and I thought like maybe these are like
Geometric just means that the errors are reduced by a constant factor, which happens to be gamma. Okay? I didn't mean anything else by it.
okay. I was trying to understand. Like,
I think, okay, important point. I can use words in ways that you don't expect them to be. And yeah, be brave like Alex and ask clarifying questions, because I might say geometric convergence, I never defined it. You don't know what it is, you can ask.
yes, I wasn't sure if you meant geometric and like you have like it's like you take the gradient is like an exponential function. So.
No.
Okay.
I just meant what I said. No.
Okay.
Okay. All right. So especially in these summaries, if I'm saying things like if something's not clear, just ask. All right. Good. Thanks, Alex. All right. Is this clear?
I think there was a question in the chat about why we use the max norm everywhere.
Haha. Yeah. Well, it happens to work. I guess maybe the question is, could we use something else? I think we want to use anything that works. The fact that the max norm works is because of a number of things. Like all the operations that are involved in the definition of this operator T. So the T operator is something like this. There is a maximization, there is some reward, there is some affine combination, there is some linear operator applied. So T of V is equal to M applied to R plus gamma P V, where M is maximized with respect to actions. And so when you go from V to PV, this is a linear operator. This is stochastic. Stochastic operators are one norm non-expansions. Awesome. Multiplying with a constant makes the constant multiplication operator itself is Lipschitz with that constant, which means that if this constant is less than 1, then this is a contraction. This happens to be true for any norm, so there is no restriction there. And like what we're doing here is that if you're composing operators, so these are going between different spaces. So there is the V space, and then if you apply P to it, then you go to the Q space. You apply the multiply with gamma. Okay, multiply with P. Then you're still in the Q space. Then you add R to this. So that's like a shift. That's an affine operator. It's a non-expansion, of course, in any norm. So that's still the Q space. And then the M operator that takes, some action value kind of thing. So a function that applies to any action value real, and it maximizes over the actions for every of the states. That goes back to the V space. This is a bottleneck. If we chose some other norm, this is very likely not a non-expansion. But for the infinity norm, it's a non-expansion. So non-expansion, contraction, non-expansion, non-expansion. decomposing all of this, you get the best of all. Like in general, it's like if you have some Lipschitzness happening with some operator, you compose the operators, then you have to multiply the Lipschitz factors of the operators. Prabhat.
So we can think of like n steps of value iteration as like finding, I guess, the optimal value over n with our horizon of n, right? And I guess that's why this bound looks like the discounted return bound from earlier in the notes.
That's right.
So if you happen to like know statistics of like episode length, would you be able to like strengthen these bounds?
I don't know what you mean by statistics of episode lengths.
So for example, if you knew like if you knew an episode was going to terminate within 100 steps, then you could just stop value iteration after 100 steps, right? And your error would go to 0.
I don't know what you're saying. Let me try to understand it, unpack it. Are you saying that we are in fact in a finite horizon problem? What does it mean that an episode terminates after 100 steps? If it happens to no matter what we do, then we have a finite horizon problem with this episode length of 100, right? That would imply that. Then we want to solve that problem. Then we don't necessarily want to solve the infinite horizon discounted, return maximization problem.
Yeah, so I guess what I'm asking is, I mean, maybe it's not very useful in practice, but let's say we could say a specific, like for a specific horizon, there is a probability of termination, right? So maybe after a horizon for a horizon greater than 1,000, we could say the probability is this value of terminating, right? So it's not necessarily a fixed horizon, so not necessarily a finite horizon problem, but if we had statistics across horizons. So let's say, I don't know, a horizon of 100, and we had a normal distribution. Actually, no, you can't have a horizon of less than 0. But
sure,
some distribution from 0 to infinity over horizons.
I don't know what's the meaning of that, but maybe let me have to. I try another take. So are we still talking about discounted infinite horizon problems, just speeding up calculation?
So yeah, infinite horizon problems with termination probabilities for each horizon.
So they do have some extra special structure.
Yes.
The termination would mean that you go to a goal state, and then from that point on, let's say you're not getting any further reward or something like that.
Right.
But otherwise, it was infinite horizon discounted. Okay. Right. And then maybe, well, the termination probabilities for each of the horizons could depend on which state you're starting from, what policy you used. But maybe you could use this extra structure to your advantage, that you're terminating and then you will not get further reward. If you had some extra piece of information to speed up calculations even further, I can imagine that. Yeah, if that was your question, yeah, that's possible. I don't know whether the gains, maybe there are cases when the gains are sufficient to warrant worrying about this. This geometric convergence, yeah, okay, let's talk about that. I wanted to say the geometric convergence is pretty fast, but that's true if you fix the gamma, and the gamma is the discount factor is going away from 1 in a reasonable fashion. But if you take, gamma to be, I don't know, very, very close to 1, so it's 1 minus 10 to the power 100 or something. It doesn't even have to be like that. But 1 minus 10 to the power of, I don't know, 5. Then the 1 over 1 minus gamma. The 1 minus gamma now is the 10 to the power of minus 5. And so suddenly that blow-up factor is huge. Like it's 10 to the power of 5. So it's in the eye of the beholder of whether geometric convergence is fast or not. So why are we talking about this 1 over 1 minus gamma? Because this is the characteristic time of like how long does it take roughly to get to your answer in the lack of extra structure. So if this 10 to the 5 or whatever number that is going to be is too large, then maybe you need to look for further structure. And yeah, and very often we are interested in large horizons. So it's a relevant question.
Doesn't this kind of also hold for the finite horizon case? Like if you're in a fixed horizon and your horizon is at 10,000, you have to do 10,000 steps of value iteration.
Right. But
In
maybe you can stop earlier.
Huh?
But maybe you can stop earlier. That's right.
Well, wouldn't you have to do like some kind of backwards induction? Like you actually have to, because you have to solve it for h equals 10,000, then h equals 999.
Yeah.
And
Yeah,
if you stopped it early, you wouldn't have like what the value at h equals 1 is, type of deal.
But maybe you can organize the calculations in some other ways, right? Like maybe forward draws, backwards, like back and forth. I don't know, like some crazy stuff. There is a lot of algorithms out there that are trying to cut down on the cost of calculation even further.
Do they work? Oh, is it this polylog stuff?
No, it's more like instance dependent. Like in the worst case, you can't really save much, I think. Although we'll come to this, but I think that this 1 over 1 minus gamma factor is real in a worst case fashion. Because every time, okay, so now let's go to the next slide. So next slide is saying, all right, so if we are thinking about calculating a near optimal, a data optimal policy, a policy which satisfies this, so that would be data optimal. How long does it take to do that? You plug in everything, and then you try to do it with value iteration. You get this number. It's square number of states times number of actions divided by 1 minus gamma times this log 1 over data. Data was your precision. And you should ask the question, is this real? Or could we do better? Can we remove, I don't know, like the 1 over 1 minus gamma factor? That seems to be very sum, or the S, or the A, or whichever, right? Like you can ask all these questions. And I don't think we have an answer. But maybe it could be a good project to think about whether you can get a lower bound that involves S, A, and 1 over 1 minus gamma. I think you can. Maybe, yeah, one has to dig a little bit the literature because people looking at the average cost are bumping into this problem. Somehow, letting gamma go to infinity is kind of modeling gamma go to infinity, gamma go to 1. Like, let me know if I'm talking nonsense. Gamma go to 1 is like the average cost problem. So in fact, if you take, so this v pi, let's make the dependence on gamma explicit in these value functions. If you start to normalize it, and then if you're lucky enough to have sufficient structure, then this is going to converge if you normalize it. So the scale, so this guy here, this could be as large. It's not necessarily as large, but could be as large as 1 over 1 minus gamma, right? Like every step you get a reward of 1, then it can go that high. So that's unnormalized. But if you start to normalize these by pre-multiplying with 1 minus gamma, which you can also think about, okay, it is just like with a geometric probability you're picking which time point you want to be at, right? Like you want to pick time point k with probability gamma to the power of k. And then the normalizing factor to make this a probability distribution would be just like this 1 minus gamma. And so that's a way of calculating an average. It's a weighted average over time. Okay, so now we're calculating a weighted average. And so if you have some regularity in the MDP, then as gamma goes to 1, this is going to go to the value function for the average reward setting. And so gamma goes to 1 in a way kind of models the average reward setting. So this is called the vanishing discount approach. So one of the reasons we care about the gamma goes to 1 case is because we want to think about the long horizon case or the average reward case. And then the question is, okay, is this real? And so I was saying that I think in the average reward literature, there is some indication that this is real. I think it's real, and you cannot improve it. But I didn't see a very clean presentation of this result for the discounted setting at all, which is unfortunate, given how fundamental this question is. I mean, okay, truth to be told, this is all nice, calculating stuff with a finite MDPs. We need to understand these things, but this is not, like the ultimate goal is not this. So we shouldn't spend an infinite amount of time on this either, because we want to go to the problems where the number of states is so large that this amount of calculation would be ridiculous at, right? So you can't like just visit all the states in the world. Like that's nonsense. But before we do that, this is a warm up. We're trying to understand what you could do in when the number of states and actions is not too large. And then, okay. What?
Yeah, so in the average reward setting, they don't have a discount factor, right?
They don't. Yeah. It's kind of
So where is that discount factor coming from in their lower bound that you were saying? Like,
No. So they have something like a mixing rate for the MDP. But the mixing rate is, I think, a more fundamental quantity is the span of the value function, the span of the optimal value function. If the optimal value function has a large span, then I think the calculations are gonna take longer. And the span kind of it's related to the mixing, and this whole convergence only happens if the span of these value functions, the normalized value functions, can be kept bounded as gamma goes to 1. And very often what happens in MDPs which are not too nice, where this average reward is ill-defined, that this span is like explodes. And so those would be hard instances, and the easier instances of these MDPs, as far as gamma goes to 1 or long horizons are concerned, are the ones where the span is kept finite. And there they have not quite a span, but something related to the span in the lower bound. So that's why I'm saying it's not a fully finished business. And I think that there is a lot of opportunity to improve things there. Okay.
I was going to ask a question. Does how you mentioned like a lower bound for like this 1 minus gamma business?
Yeah.
Is there like a lower bound that somehow depends on this quantity? Like, let's say there's this quantity gamma star, where you can imagine, like, let's say you have a small 5-chain MDP, like deterministic chain.
Yeah.
And like, if you set gamma to be like 0.1 or you set gamma to be 0.001, the optimal policy would still behave the same.
I guess you're saying 1 minus 0.1 or 1 minus
yeah.
0.1.
Sure, like it almost like
Like the gamma should be close to 1, because if gamma goes to 0, then
Yeah.
okay.
So yeah, you can imagine, like you set gamma to be maybe like 0.1, and then you let gamma go to 0, but it doesn't really change the behavior of the optimal policy. It's almost like your planning horizon is overkill for this small MTP. Like you're planning too much. Does that make sense?
Yeah, I'm like, it can also be that on some instances you're like, this is an overkill. Like, we are interested in first approximation, but in the worst case, the 1/1 minus gamma should be there. The best is no, because in the best case, everything is an overkill, because you just take the rewards to be identically 0, and every policy is doing equally well. You shouldn't do any calculation in this case, right? Like the best case, you don't have to do calculations. That's kind of silly.
So I guess the instance would be like this: what's the minimum amount of planning you have to do before your optimal policy stops changing? Like you almost like the behavior of your policy.
Oh, but like here, we also wanted to have some arguments that are independent of what algorithm you're using. It shouldn't be value iteration dependent.
Yeah.
It's like,
so,
you just want to know, like, fundamentally, can you get away with less calculations than whatever is shown here? So it's like, there's no iterations. Like, I don't know what this algorithm is gonna do. Let's go to some further slides, because it's gonna clarify some of these things. There we go. So this actually is the lower bound, and it shows so the lower bound just says that you have to touch basically every state action pair S times before you get an answer. And this is expressed in terms of the number of elementary arithmetic operations. But there is no gamma here, and the data dependence is not shown either. So if you want data optimal policy which is small enough data suboptimality level, then this already kicks in. And but the lower bound is expected to grow with data going to 0, maybe, or not. Well, based on previous result, we would expected at least some log 1 over data or something. But there is no data dependence here. So the first question is, should there be a data dependence? The answer turns out to be no. And to get to this answer, let's just recall what policy iteration is. It's a slightly different thing. So in value iteration, so we were doing this thing that there is V star, and there is this vector field, and then we are just like moving along the vector field to V star. And then after every step, we could, look at the policy space. So this could be pi space or something, blob. Then you can take the greedy policy with respect to these, and you would get guarantees that these policies are improving. But this space is a little bit unstructured. Like, there is not much point of like showing points here, and because the ordering of policies is based on just the values that they produce, it's like, okay. So maybe the policy should also be represented here, so that then it would be that, like, okay, the policies are jumping around, so the value functions of the policies are like that, but they cannot. They also have to improve at the geometric rate. It's just like there is a blow-up factor of age, roughly. So I will call this 1/1 minus gamma the effective horizon, just age. So that was value iteration. And then with policy iteration, it's a slightly different picture. So you in fact start with, I don't know, okay, so there is this space of policies. You start with a policy, and then you jump into the value space, and then you greedify. You jump back, and then jump back to the value space by awaiting the policy, and then greedify, jump back. And it turns out that this process is also improving, like at the geometric rate. That's very easy to see. It cannot be slower than value iteration. This is the whole process. It's called policy iteration. And it was, I think, discovered by a person called Howard, who also wrote some nice probability theory book, or maybe books. And in one of them, there is a very nice description of MDPs. I discovered that when I was a PhD student. It was beautiful. Anyways, so what's true for this policy iteration is that after only this many iterations, it discovers a policy which is optimal. Okay, ties have to be resolved in a systematic manner. That's all. So that means that if there is in the greedy operation, you need to choose between two actions which are both maximizing. And previously you choose one of the actions, then you have to keep that action. You cannot switch between the actions, because then you can just like jitter and you will never converge. And yeah. So these many iterations, after these many iterations, the policy is optimal. So there is no, like, if the accuracy is small enough, then you would think that this log 1 over data, so this was the data accuracy, one data suboptimal policies, then this is blowing up as data goes to 0. So you would think that the effort needs to increase, but here is a result that says that the effort doesn't need to increase. So at one point, as data is really small, you are demanding the optimal policy, and this guy is going to find the optimal policy. You kind of like bump into that. It's like a magnet. Excellent.
Oh yeah, so the runtime of computing VPy is not included here, right?
Yeah, if we include the runtime of computing VPy, then this is the estimate of the number of operations that you're gonna need. So it's s to the power of 4 times s cubed a squared times age. So this should be compared to what we had previously for value iteration, which was s squared a. So compare with s squared a over 1 minus gamma times log 1 over data. And this tells you everything that people ever said about the relation between value iteration and policy iteration and more. So for really, really high accuracy, policy iteration definitely wins because this is unbounded. But for low accuracy, because value iteration is cheap in the way it iterates, and it's still making pretty fast progress, for low accuracies, value iteration could win, right? So it's kind of interesting. I don't know whether these differences are actually real. So whether you can come up with an example where these differences would be exhibited, probably they are real. Yeah, but
Yeah, so going back to the lower bound where you started off with mentioning whether we need to introduce that delta in the lower bound, and then you answered it by saying that we don't because of the policy iteration bound.
yeah.
But that's not exactly true like you're saying here, right? It's just that if we're okay with like incurring this extra cost of iterations that the state, like in the state and action space, then we don't need it anymore, right? So there's still that question of whether that delta is required if we would just like to incur state squared times actions in terms of iteration. correct?
I think I wouldn't phrase it like that, but there is the question of what is the instance dependent complexity, where in the instance maybe there is also a delta or whatnot, right? Like if you want, you can give an accuracy, and maybe the algorithm should be given the option to stop earlier, and then maybe it could save some calculations. So the input should be data and all the tables that describe the MDP, and then you want to have an algorithm, and then you want the best runtime, no matter what the instance was. But this is too hard. This question is too hard to answer. Just think about how much do we know about how long does it take to multiply two matrices? Do we know the answer to that? Well, we have upper bounds, right? It's like, let's say square matrices. How long does it take to multiply them? Cubic, right? But that's an upper bound, and you can reduce it. And we don't actually know the actual exponent, and that's just worst case. And here you would be asking for something even finer than that. So I think that these are good questions, but it's definitely beyond my pay grade to answer any of these. It's really interesting, but we should probably first work out how long matrix multiplication takes before trying to answer these questions. I might be wrong that maybe these questions are easier to answer, but like I have the feeling they're not, right? In
Yeah.
fact, we need to multiply matrices with vectors here. So that's kind of the same business. What do
Yeah.
you want to?
I was gonna say, like, yeah, I guess we don't have like obviously a matching lower bound for matrix multiplication. I got it's a very side note, but is it just like the current best is just like to the power of 2 of the dimension or something?
I mean, you have to write down the result. That's
Yeah.
this. And for every entry, you like the trivial calculation is cost you d, so that's d cubed, right?
Oh, right. But then how do they drop it down to like 2.3 or something?
Yeah. So that's like using blocking and very clever techniques, right? So it's a branch. It's not branching bound, but it's like decomposition, problem decomposition, and recycling designs. It was Gauss's idea, of course, not for matrices, but for complex numbers. He noticed that you can multiply two complex numbers with less than the trivial number of operations by just staring at it for long enough and rearranging the order in which you're doing the operations. Because he was really obsessed with calculating things fast.
So
I
then the
guess
lower
if you
bound
call and anyways, yes, in the lower bound.
but yeah, then the lower bound can't be d cubed, right? Unless it's like
No.
restricted to
Yeah. So we already know algorithms with, I don't know, 2 point something complexity. I forgot the exact exponent, but it keeps improving, and we don't have a lower bound. And we do have a d squared lower bound because you have to write down the result. That's trivial. And that's sort of this result is almost the same, right? Like you kind of have to write down and multiply and like look and like it's kind of very similar. But it's weak. But maybe some people think that d squared is the truth. But this also goes back to how you're representing your input. So we are getting into, I don't know, questions which are interesting, yet maybe, I don't know, too particular. I feel, okay, so you cannot say that for matrix multiplication, but here with MDPs, it turns out that if we're representing the probability tables that correspond to transition probabilities in different ways, you can speed up calculation. Okay. That's all right, but it's becoming very, very particular. So yeah, so reducing exponents in upper bounds is fine in this poly results. That's a Versi um, enterprise. At the same time, trying to match with lower bounds the poly results. That's a cruel requirement, I think. It's just too much. It depends on so many things. All right. So the key to this result, and this is something to keep in mind, is this value difference decomposition or identity. It's just like you take the definitions literally of the value functions, and then with 2 lines of algebra, you arrive at this identity, and it's going to be used everywhere in the course. A lot of the cases, we're going to replace the state value functions with action value functions. Then you can buy the same thing. It's very useful, and it's the basis for many different things. All right, discussion. So I thought that, okay, so we do have a bunch of points. So there is the simulator knot that I brought up the last time, but we can postpone it. You can think a little bit more about it. I think eventually we need to discuss this. And I thought that the structure should be some breakout rooms, blah, blah, blah. Another discussion point would be computational complexity. So when we're talking about the complexity of the algorithms, we're counting arithmetic and logic operations like max of 2 numbers counts 1, adding 2 numbers counts 1, multiplying 2 numbers counts as 1. So what is this? Like, is this the computation model that you learn about in school? Is this what we should be using? Um, if we use some other model of computation, what would be another model of computation, by the way? Can someone tell me?
Something parallel, highly parallel.
Okay, that's fancy. I was thinking about something, like com uh, Introduction to the Theory of Computation 101. What would you learn about there?
Is it like steps on a Turing machine?
That's right. That's also called a binary computation model for reasons, because there somehow the size of the input as written in terms of how many bits it has is what matters. Because the Turing machine needs to read all these probability tables, and they have to be written in every cell, and like you can only have a 0 or 1. So it's like that's the binary model of the computation. And now you might be wondering about which model to use, and are there any consequences of flipping between the two? So this is one discussion we could have. And we do have some questions from Slack. We have 10 minutes. I don't know. How do we feel about this? All right. I think we don't have too much time. So I will just go for the questions from the Slack. And maybe next time I will try to reserve more time for discussing some of these topics that I raised today. And then you can, in the meanwhile, just think about them a little bit. So questions from Slack. Kushagra, do you want to ask your question?
Sure. So I remember in the lecture you talked a little bit about the heaven and the hell MDP to prove
Mhm.
this the lower bound for iteration complexity of policy iteration. So
That I think it was heaven and hell. I think it was algorithm independent. I think it was just like, no matter what algorithm you use, it cannot avoid of reading all these numbers. That was the argument. That was the argument I was trying to make.
Okay. Okay, I see. Um,
Yeah, just
Yeah.
also one point is, yeah, it was algorithm independent, and I rewatched the lecture, and I think in that lecture, Chaba had described a different MDP than in the lecture notes, and I think the one in the lecture notes is the correct one, and then I think you might have made a slight mistake in the lecture, like video, but yeah, because maybe that's your other question, because it was slightly different than the lecture note version.
One general thing is that the lecture notes are always more refreshed than what the lectures were. And so very often, even if, like, it can happen that in the lecture something was not quite right, I definitely try to fix it in the lecture notes. But maybe even if something was right, maybe it's rewritten in the lecture notes in a way that makes it cleaner and more clear. And so the lecture notes may help you in this case. Yeah.
Yeah, all right. And yeah, I guess there was another follow-up question, but which is very similar. But I think it might be corrected in the lecture notes. That in you said that the iteration complexity would be k star multiplied by sa minus a.
Yeah,
In
that
the
was incorrect.
yeah. I guess yeah.
Yeah, yeah, it's corrected in lecture notes. This
Uh,
is the problem with these recordings.
yeah. I guess yeah.
Yeah, and I think the lecture after that, when we go over the actual proof, we put it down, it's written the right way, which is minus s there, because I
Okay.
also rewatched that. Yeah, but good point.
Thank you. Okay.
Yeah,
Thanks
that's a
so
good
much.
point. Yeah. All right. All right, Prabhat.
Yeah, so in the discounting section, we sort of derived that the H star from
The
I
way
mean
you
you
found.
yeah, well I think it's even done in the discounting section, like the difference between the
Yeah.
infinite horizon and then it says like so you have this H gamma epsilon, so without the star, and
Mhm.
that's an upper bound on H star.
Mhm.
And so we get like H gamma H no star is greater than H star, but sort of the original bound said H is greater than H star. So
Right.
I'm wondering if we have.
Yeah, yeah. So no, we're
Go
not
ahead.
concluding this, but we are going to demand this, which is going to imply that H is also bigger than A star. So nice things happen if H is bigger than H star. So if we demand something stronger, mainly that H is bigger than H gamma epsilon. Since H gamma epsilon is bigger than H star, then H is going to be also bigger than H star. Then the nice things happen. That's just the logic of it. Like that's what I wanted to say. All right. So it's not implied.
So it's a requirement that we
Yeah, we're
require.
imposing a stronger requirement because it's simpler to state.
I
That,
see. I see. Oh, okay. And so and we just require this stronger requirement because it just makes life easier.
yeah, and the price that we pay for it is negligible.
Okay.
It's easier to write and remember. Like every time you would not need to write this log 1 over gamma. You just write 1 minus gamma.
Okay. And okay. Thanks. Yeah, that answered my question. And then the relationship between those two is that their ratio goes to 1 as gamma
I
approaches
think
1. I
it's
think.
okay. So let me try to figure it out. So there is H gamma epsilon, and that's bigger than H star gamma epsilon. And both of them are of the size of 1 over 1 minus gamma of the constant factor. Okay?
Okay.
So if you take the difference between the two, then you get something that's bounded by, lower bounded by 0. And both of them are of the size of 1 over 1 minus gamma. Okay. So there were these two numbers between 0 and 1 over 1 minus gamma. There was one number here. This is the h star of gamma. And then there is the, okay, there's a constant here, right? And there is the h gamma. H gamma is a slightly bigger guy. And we take the difference between two, and we let gamma go to infinity. Of course, the length of this interval explodes, that both belong to. So we renormalize with that. So if you multiply with 1 minus gamma, this difference, okay, and you look at this difference, it's lower bounded by 0, and you can also show that it goes to 0 as gamma goes to 1. So in a way, relative to the size of the interval, the difference between the two is vanishing. So it's really, yeah.
Thank you.
Okay. All right. I think that's it. And well, we have 1 minute that we spared. I think I can give you back that. Took more of your time last time. All right. Thanks. I hope everyone had a great time. See you next week. New assignments are out. Have fun with them. Ask the TS if you have questions, or just ask questions on the Slack channel. Okay. See you.